highlights of your experience in Moscow since you brought it up?
Well, the joy was being able to go back and forth between the two cultures during the depths of the Cold War. It was interesting that the CIA and FBI never came around and asked me about what I was doing, even though I was working hand in hand with the people who created the Russian hydrogen bomb. But this was 10 years after they created the Russian hydrogen bomb, Andrei Sakharov and Yakov Borisovich. But the issue was that they asked my friends, and my friends told the FBI and CIA he will not cooperate. And his link with the Russian physics community is very important for communication between the two physics communities. By contrast, my Russian colleagues were debriefed by the KGB every time I met with them. And that was the difference between the two countries in sort of a nutshell.
Anyone else have any questions?
What is your take on the multiverse hypothesis?
So I think it's very plausible. I want to know the answer. I don't think we'll know the answer until we have the laws of quantum gravity. And these laws of quantum gravity, most physicists think the best approach at the moment is something along the lines of so-called string theory or M theory, though loop quantum gravity is also promising and might turn out also to lead, or instead to lead to the answer. But these missing laws of quantum gravity are the things that will tell us about the birth of the universe, about what went on inside black holes, about the multiverse, and about whether you can build a time machine to go backward in time. And so that's the most important, most exciting area of physics so far as I'm concerned, and I have never worked in it. And it's because it's too crowded and I need elbow room. I would be miserable working in it, even though I think it's the most exciting thing, just because of my personality.
With the Higgs boson particle being proven within recent years and now gravitational waves being proven, what do you think the next big potential thing that could be proven in physics, what would that be?
Well, I think the most important thing will be huge surprises. The Higgs particle was expected. Gravitational waves were expected. When our team discovered gravitational waves from colliding black holes, I had not a sense of excitement, but just a sense of profound satisfaction because I knew it was coming. I knew what was coming. But there are going to be huge surprises from gravitational waves in particular, because every time we've opened a new window onto the universe, we've looked at the universe with a new form of radiation, we have seen big surprises. The world through optical telescopes, or the universe through optical telescopes, looked serene. Through radio telescopes, when radio telescopes came online basically in the 1950s, began in the late 30s, but really the 1950s, it became evident that our universe had a very violent side, huge explosions in the centers of galaxies. Each new kind of radiation has given us big surprises. Gravitational waves are radically different from all the other forms of radiation. All the other forms of radiation are electromagnetic: X-rays, X-ray astronomy, optical astronomy, radio astronomy, infrared astronomy. It's all electromagnetic waves. It's all oscillating electric and magnetic fields. Gravitational waves are made of ripples in the fabric of space-time, wildly different. So opening the gravitational wave windows is like Galileo pointing an optical telescope at the sky for the first time, and we will have all these new kinds of gravitational wave detectors looking at different wavelengths. There are going to be enormous surprises with this new kind of radiation, and that's what, to me, more than anything, drove my work on this, is to open up a new window, but also I wanted to see geometric dynamics, but mostly I want to see the surprises that come, that tell us that there's something about our universe that we just didn't understand at all before, that is radically different, that will make our understanding of the universe be very different 50 years from now or 30 years from now from what it is today. I don't know what those surprises are going to be. I would tell you if I knew.
I have a question actually for you.
Yeah.
So like CERN, the Human Brain Project, the Human Gene Project, all these are like very, very big works of science. In your experience, how effective do you think like huge, big kind of works of science are, rather than kind of a cottage like industry, like small experiments?
If there's something that can be done small, that's the way to do it. But there are certain things that cannot be done small. LIGO could never have succeeded as a small project. It had to have this kind of size. It was so difficult. The instruments are so complex. And that was evident already in the 1970s. Vladimir Braginsky, whom I mentioned, my Russian collaborator, he's a superb experimenter. He remained, although he believed that in principle you could build these gravitational wave detectors, he thought they would be so complex that you would never succeed. And he kept telling us this until the late 1980s when he saw the progress that had been made. And when he saw that, he shut down everything else that was going on in his lab and he joined the LIGO project. But he, for me, was the touchstone of good sense about experimental physics. And he was an example of wise caution for quite a while. So we had to go big. You just couldn't do it any other way. And as I say, it was obvious from the 1970s onward. And similarly in the other areas, I presume that I don't know as well, but certainly Higgs boson, you had no choice but to do that with big science. In biology, there has been some problem adjusting to small science and big science alongside each other. In physics, we learned to do this long ago, and although there's a bit of unease between the condensed matter physicists who work in small science and something like high energy physics or LIGO, we have learned that some things have to be done big or they won't succeed, and if they're sufficiently important as LIGO was or as high energy physics has been, you do it. But you make sure that you sequester adequate funds for small science alongside it so that the funds don't get eaten up by the big projects. In astronomy, they haven't learned that very well, and small-scale astronomy, particularly theory, has been badly funded compared to the big projects. They've not done the sequestering, at least in the US, that has tended to be done more successfully in physics.
Yeah, that's good. Any other questions?
What's your take on quantum entanglement, if you've heard of it, with the research that Royal Rife did? I don't know if you've heard of that.
So I don't know that particular research, but quantum entanglement is a key to quantum non-demolition. You entangle two photons together in a particular way that enables you to beat this Heisenberg uncertainty principle, circumvent it. Quantum entanglement was first recognized, I think, by Einstein, Podolsky, and Rosen in the mid-1930s in a period when almost all the rest of the physics community said that Einstein was a has-been, that he didn't understand quantum mechanics, and that they sort of made fun of him. But this quantum entanglement that he identified as being a really big deal turned out in the 1990s and onward to be tremendously important for modern quantum information science, for quantum non-demolition in our experiment. He was a lot deeper than in quantum theory than the people of his day realized. And so all I can say is quantum entanglement is crucial for 21st century technology when you're doing really high precision measurements. It's the future.
Any more questions? Yourself?
Is there a distance to these colliding black holes that you can get where you perceive the wave passing through a human being?
So I didn't quite understand the question. I mean.
So if you're traveling in a spaceship
somewhere
in the universe and one of these goes off,
yeah.
Is there a distance where you notice it?
Where you would feel it?
Yeah.
Yeah. Yes. If you're close enough, you will feel it. If you really want to feel it properly, you don't want it to oscillate at 1,000 hertz. There's a bad impedance match between your body and and a 1,000 hertz or a 100 hertz wave, you want it to oscillate around 1 hertz or a few hertz, then you'll really feel it. And so that's what you will get if you have two black holes that are, say, 10,000 solar masses that collide and merge. You'll get waves of that frequency, and then you would really feel it. It's not because the holes are bigger and making a stronger force. You put yourself farther away so that you're in the wave zone where you're really looking at waves, but then you really feel it because it matches to the natural frequencies at which your body is going to respond and stretch and squeeze and feel very, very uncomfortable. And then if you do that then and you're in the inner edges of the wave zone, you'll be uncomfortable.
Anyone else? No. Oh, yeah, here's that.
So Kip, I've read a bit about you, and I've read one of your, in I think it was 1997, you were kind of talking about how you thought, like, in the 21st century, dark matter would kind of be one of the, like, biggest kind of advances we made. I'm just kind of wondering, like, where do you stand on that, like, in 2016? What's your kind of, how do you feel the field of of studying dark matter and, that side of the universe is going to, like, develop over the next few years?
Well, I think the mystery of the nature of the dark matter and also the so-called dark energy, these are very important mysteries for fundamental physics, but also for our understanding of the universe. The best guess today is the difference between dark matter and dark energy. Dark matter gravitates, it clumps down around galaxies. And so it has to be something that moves at low speeds. If it was made of particles that moved at high speeds, it wouldn't be able to clump down under the gravitational pull of galaxies. The dark energy has to be spread more or less uniformly through the universe from its properties. It won't clump. So these are two things that make up most of the energy in the universe, dark matter and dark energy. The kind of matter you and I are made from is like 4% of all the mass in the universe. So to have 96% of the mass in the universe be in a form that we don't know what it is, that's a very important puzzle, both for our understanding of the universe and our understanding of fundamental physics. Dark matter is probably some type of fundamental particles that don't interact very strongly or at all with ordinary matter except gravitationally. Figuring out just what it is it's going to be an eye-opener. Even more of an eye-opener perhaps will be the dark energy. So those are really important problems. Yeah.
I believe there's another question. Yeah.
Mm-hmm.
Since you brought it up, what can you tell us about the next movie?
Okay, so the next movie involves different physics than Interstellar. Interstellar was primarily warped space-time, general relativity. It's a movie, and so I started Interstellar together with an ex-girlfriend of mine, a former girlfriend of mine, who's now a close friend of me and my wife. I should add. Her name's Linda Obst. She was just beginning a movie career in Hollywood. She had been a science editor for the New York Times, so she had a science background, though she was a philosophy major in college. And Linda was working on her first movie where she had the idea for the movie, and it was called Flashdance, which was a big hit around the early 1980s. Then she made Fisher King, Sleepless in Seattle as a producer, How to Lose a Guy in 10 Days, and Contact. She's very versatile. The Art of Lying, a huge number of well-known movies of wide range. And so she phoned me up one day and said, would you like to brainstorm with me for an idea for a movie? We brainstormed and it became Interstellar. And she brought the Nolan brothers on to write and direct it. They completely changed our story but preserved our science. And so our goal in making Interstellar was to make a movie where we built the science into it from the very beginning, deeply into the fabric of the movie. And so the movie was as accurate as you could make it in terms of the science while still making a great movie. And that was a goal that was embraced by the Nolan brothers, by all the main actors in the movie, and I had personal conversations with all of them. Anne Hathaway, Matthew McConaughey, Jessica Chastain, Michael Caine. And so they all embraced this, and it was their first experience trying to do it, as well as my first experience in a movie. And so, well, you know, it came out, it reached 100 million people, and it was a great fun, as well as achieving the goal that I wanted. And so the next movie, I have co-authored the treatment with Linda Obst again and with Stephen Hawking. So we brought Stephen on board for this movie. We co-authored the first draft of the treatment several years ago and then put it on the shelf while Interstellar was being made and have returned to it since Interstellar came out. We now have a director, we have a studio, and are negotiating with a potential screenwriter that the director and Linda are enthusiastic about. As am I, though I don't carry any weight in the choice of a screenwriter, but I've met him and I'm very impressed. But I can't tell you anything more than that. And that is because, as I learned in making Interstellar, the studios are highly skilled in leaking information about a movie at just the right rate to optimize ticket sales. And they don't want me to interfere with that leaking process. And my contract says I will not interfere with that leaking process. I will not reveal anything beyond what I have been authorized to say. I've told you everything I can tell you, aside from telling you my guesses. It's just a guess based on experience with Interstellar. The movie will come out at absolute fastest 3 years from now, and at the slowest perhaps 7 years from now, unless it completely dies, which I don't think it will, given the people who are involved. So roughly 3 to 7 years from now. And it will be a mostly different science from what you saw in Interstellar. And it will be fun, it will be scientifically intriguing and exciting. And knowing the director and the potential screenwriter, it will be a great movie. It will be a blockbuster.
Really great question. I think one final question, and then we'll be off.
You just said that you tried to make the movie as scientifically accurate while still telling a good story. What were some parts of Interstellar where the science sort of broke down and wasn't as accurate as it could be?
So I'll tell you the most inaccurate piece, and then I'll tell you where to find out all the rest. Okay. So the most inaccurate piece was this. There's a trip through a wormhole, and the wormhole was designed very carefully to have the kind of appearance that Christopher Nolan liked. You can adjust the shape of the wormhole, the size of the wormhole, and so he under his guidance, we made that adjustment until it looked really just the way he wanted from the outside. And then the other thing I forgot to say is, all of the astrophysical images that you see, the black hole, the wormhole, and so forth, those are made by solving Einstein's equations for the propagation of light around the black hole, through the wormhole, and so forth, in warped space-time. And so what you see is what it would really look like to an IMAX camera in that environment. And so the problem was then that when they did the computations, the simulations, computer simulations of what looked like making a trip through the wormhole, the trip was very fast and very uninteresting. I could show you what that looks like in another talk. Well, I've got it on my computer, but I don't want to take the time. It was a very fast trip, very uninteresting trip. And so Christopher Nolan, after they were finished filming, when he was starting to integrate the computer graphics with the movie, and he was just getting the results of these simulations from the team in London, he called me up and he said, "We've got a problem. Would you come over to my house and let's discuss it?" So I drove over. He lives about a 20-minute drive from me. And he sat me down in front of a giant computer monitor and showed me what this wormhole trip looked like, and then trips the wormholes that had other shapes, which she had then requested. None of them were very interesting. And he said, okay, now what do I do? And I said, okay, this is where you use artistic license, you depart from the science. And so the trip through the wormhole, if you want to go back and watch the movie on DVD, say, it's accurate up until the point where Cooper, Matthew McConaughey, pushes the joystick to enter the wormhole, and then it departs. And what you see is an amalgam of images from different simulations put together and then distorted, and a lot of sound that wouldn't be there. So that was the one big departure. If you want to know all the other departures that I was aware of at the time I wrote my book about the science of interstellar, you go into the index of the book at the back. I like to do this. This is in all the books I've written. Basically, I have things like this. You go in there, and you don't look under the subject index. You look under the. You don't look in the author index. You look in the subject index. And in the subject index, you look up a name, Christopher Nolan, in the wrong index. So you look up Christopher Nolan in the subject index. Then you scan down through there, and you'll see compromises that Christopher Nolan made with the science in order to make a great movie. And I don't know if anybody has ever found that entry without my telling them, but then you find the list of pages in which these compromises are discussed.
Perfect. I think we're just going to
Okay,
present
fine.
with the medal, and then that's it.
Well, thank you very much. It's a great honor,
No,
and I'm
you're very
really
welcome. Actually,
pleased.
one
Thank
round
you.
of applause for Kip.
Thank you very much.
You just want to get a photo?